Right, so using the light or not let's start today's section with Clécio. So Clécio is going to talk about gravitational waves. So yeah, please, Clécio, the stage's yours. You know, people are going to interrupt you all the time. So.
Thank you. I heard that we interrupt a lot, right? I think that's a good thing, you know? 1 hour speaking is too much. Anyway, so today I'm going to talk mostly, oh, sorry, I forgot that I can't see the pointer. Mostly about the work.
The pointer, where's your stick?
This,
It was here.
this is only for tall people.
There's a sticks on north.
I guess mine, we can.
But anyway, I can live without it.
Okay.
Just check.
So I'm going to talk mostly about the work I've been doing this year with some of colleagues and postdocs working under my supervision in CBPF, and also the prospect for future gravitational wave in the catalog method, using the catalog method. Well, just to give a brief introduction, as pretty much everyone is cosmologists, everyone is aware of this. We are living in a big tension, in a significant tension between CMB related and supernova related measurements, or early or late universe measurements. I'm going to talk about gravitational wave, which correspond with this big and huge bars here in green. So it's a compilation of many of measurements we have from H0. There's a more recent compilation, but this is the one I could easily get. So not so exciting, these big gravitational wave error bars, but I'm going to try to explain to you how do I think it could be improved and could be competitive in the near future. So everything starts with the gravitational wave detections, right, from LIGO, Vigo, and Kagura network. So they are great of identifying compact objects, as you know. So they mostly can find binary neutron star mergers in which we expect electromagnetic afterglow, binary black hole mergers, which we do not expect an afterglow, but we'll talk a little bit more about it later. It might have some, and neutron star black hole pairs, which can also give you electromagnetic counterparts. However, none was observed up to date. There's some good models, but it all depends on several circumstances on how we're going to find or not electromagnetic counterpart. Depends on how the merger is going to happen. Depends if the black hole can make a tidal disruption in the neutron star, for instance, in order to see an electromagnetic afterglow.
So indeed, there's one without electromagnetic. There's one neutron star event merger without electromagnetic.
You mean this year?
Yeah, I don't know when, but I've seen the plots.
Yeah, it was. I mean, the final catalog is not there.
Last year, it seems.
Sorry?
30529 last year.
Last year, this run.
Yeah.
Yes, this run of live. Yes. We don't have the final catalog yet, but still, there's sort of uncertainties in the mass, which makes I'm not 100% sure at least. Anyways, so what is the LIGO is not great at localizing, because you can have tens, hundreds or thousands square degrees in the sky of area localization. So it's great of measuring the luminosity distance, so you can have a fair constraint on the luminosity distance. But in order to retrieve cosmology, and particularly H0, which is the thing I'm interested in, we need also the cosmological redshift, which is not so great. There is a lot of degeneracy in the mass in the redshift. So we need to find this afterglow, localize the event, so we can make stellar siren cosmology in the most regular way, let's say, right? And this was a great promise. So in the past, so this was the first standard siren measurement. As you can see, this is GW170817. This is the constraint on the viewing angle and in H naught. Huge error bars, as you can see, but there's just a single event, right? And the promise is, as you can see in the right side, is that we could have a percent level measurements around the next few years, but these next few years never comes because up to now, only one bright siren was seen, which was this one, GW170817. Still, we have seen other kilonova, right? Neutron star, possible, likely neutron star mergers, right? These are the three examples of this. So the first one is GW170817 on your left. So we have the GRB 211211 and the GRB 230307A, aka my wife's birthday. And she was not so happy that I was observing that. Anyway, so these two kilonova in particular were observed in long GRBs, which are an unexpected outcome for a kilonova, which shows us that we more likely doesn't really know that much about how kilonova emissions works. Since we have this extended emission GRBs related to kilonova. Some people claim that might be white dwarfs, and these two were not detected by LIGO, even because LIGO was not turned on at the time, or it's just too far away for the LIGO current limits, right? So only one kilonova observed. The forecasts are being reviewed all the time for lower neutron star merger rates. This was from 2020, right? So you can see up to 0 neutron star mergers during the whole for a year, and well, the rates still getting lower and lower. Last time I was at IAU, people were consistently talking about how the rates should be lower and lower, right? So what do we do?
White former home galaxy that you wrote before? White former? What does it mean?
Former
home galaxy.
It's something I'm actually studying with Davi here. This is the offset. It's very big. It's a big offset. One of the biggest offsets in the GRBs, as you can see. So we are trying to understand how it comes to be so far away from the likely host galaxy. It might be
Is it like in the picture there?
yes,
really?
yes. You can see the kilonova there.
It's like
And the
1
gas,
to 2 arc minutes. What is that?
it's something like 42 kiloparsecs.
Yeah,
right?
yeah, projected, yes.
Projected, yes.
Meaning for
40 kilohertz. Okay, not that.
no.
Yeah.
And the one in the middle is much lesser.
And sorry,
The one in the middle is also displaced from the galaxies, but it's
that
much
displacement it's something it happens frequently, right? But this was a huge displacement. And the one that were observed, well, no displacement,
no.
almost none, right? This is one of the things that we don't understand, the hosts of this kilonova. This seems at first as S0 galaxy, and the other seems like spiral galaxy.
So
Yes.
for that, you have like a way to determine the redshift of the kilonova, and you search in the field for redshift of closer galaxies, and that's the closer one that appears, or how it's
There was
determined?
other candidates. For this one, it's quite clear, right? Because you have the LIGO detection, it was super close, super bright. This one, I didn't get involved in the analysis. I was involved in this analysis. So what happens here is you have other candidates around, but they're inconsistent to be the host galaxy because they are likely too far away or too close. Say, what I mean by too far away, it was the one that was too far away, 3.3, redshift 3.3 or more, disregarded as possible hosts. the GRB would have to be super strong, stronger than ever seen before, for instance. So there's an upper limit on that. And the other possible host was the Magellan Cloud, which was ridiculously close, couldn't be, right? So it was also disregarded as a possible host. So yes, that's the way we determine. We don't usually determine the redshift by the curve itself or the spectrum itself, but it could be.
Are they still part of the galaxy or they're completely?
That's something we want to understand. That's why we're modeling this galaxy right now, as we speak. We would like to understand if it's a rogue kilonova, right, in space, or it's not. Well, yeah, and how it gets there.
Yeah. So if it's not rogue and if it came from that galaxy, it must have incredible speed. So
Yes,
redshift
it would be an interaction in the galactic center or something like this. It could happen. Interacting between the pair or even with another galaxy. That's what we are trying to investigate.
because the explosion is symmetric, no?
Yes, at least from the previous ones, it should be.
Or the simulations in
Maybe symmetric. Yes.
So there's no kick.
There's not enough kick to explain this. Yeah, for sure.
I don't know.
In terms of the range of the kicks,
Yes.
it's not the case. Yeah.
Mystery. Another mystery.
That's why it's fun to study them, right? So the argument I'm trying to point here is even if the LIGO detects, even if everything goes smooth, you might not see, right? So this is a paper I worked with in DS, was published this year, about strategies of putting DCAM, one of the biggest cameras ever built, right? You're gonna lose for LSST. It's a great instrument. And how, if you have pretty much unlimited time, which is 8 hours per night, would you see the kilonova or not? It depends. It depends on how bright is the kilonova. For instance, if you choose a bright and blue model, which is this first on the left, the discovery probability, which also considers how much area you can cover during the night, right? With a reasonable depth. So it's great. It seems like something over 90%. These are two strategies. One are called reference strategy. The other is the optimizer strategy I proposed, the purple one. So you could see kilonova, right? So with a great confidence level here. But if the kilonova is not as blue or bright as it was in level 17 or 17, well, the stories are kind of different, as you can see here. The probability drops a lot. And in the reference strategy, up to 50% in the nominal limit, and maybe around 60 or something % in the limit. Right, so you might not see, even if it's there, you might not see.
Well, what's the difference between the strategies?
One is I made several optimizations by filter. One is just a regular strategy people use in the past. G plus I guess, as far as I remember, covering in the 30-second exposures. The other ones is I just I select a wide parameter range and try to get the best probability of detecting it. In fact, this strategy considers going deeper in the regions where it is most likely to find the kilonova. The region of the LIGO is not equally probable. So you can, there are fields where you should go deeper, and other fields you can go shallower, for instance. This is one of the things that takes in account in these strategies.
But like, okay, so we all observed the blue one, but why? I mean, the second other one is 1904. It gives you almost 90% detection probability. So why we haven't seen this one?
So sorry.
So like this dash dotted blue lines.
Okay.
So we have 90% discovery probability, but why we haven't seen this one?
Well, that's another question. We might not be looking at the right model, kilonova model. So that's one of the things. Do you see? This assumes a model, right? If it's bright and blue. So if it's not bright and blue, you might not see, as you can see in the reddish and slow model. While making these observations, many things can happen. I've been involved in many of them. Part of the field can be obscured by the galaxy. You might be unlucky by the time because you don't control the time and it fades super fast. So you need to be on sky very quickly. I think the record I have in using a smaller telescope was something like 40 minutes from the trigger to the decision and to put on the sky. But imagine this could happen at 6 a.m. in the morning. You lose a couple of hours, right? Before you can possibly think of doing this. So many things can happen while doing this.
It's not automatized that you have, it's not fully automatized, these strategies. It's
No, it's the strategy you can deploy an automatized strategies. That's what I do in the two telescopes I work on, the CAM and the T80, doing this. But at the end of the day, is a human decision because you have a time budget to spend. So if you invest in the wrong event, you lose your time and you lose your budget and you can't find anything. There was a particular, I don't recall the name of the event, but there was an interesting event during 2004. It was very well localized. And many people were thinking about going for it. And an hour passed and LIGO put another sky map, put the event in the other part of the sky. So, an hour or a couple of hours passed and this happened. And then we were, oh my God, we didn't trigger, we didn't lose our time, was the first thought. And then we realized part of the event was over the galaxy. So many stars, many dust. So it's a tricky decision. Especially if you have a few in these big telescopes. So when you don't find it, which is almost a rule, right? What do? You can do the dark siren method, which is this method I've been working on a couple of years now. So the main idea, you can assume every galaxy in the field to have a probability of being the host. Okay, so that's the main idea. You define, oh, it's terrible not to have the you can define this beta function, which is your selection function, depending on the cuts you are doing it to select your events. You have your prior over there. You can pretty much sum up the probability of all galaxies in the future being the host and derive a posterior from that. For that, you need as completely as possible catalog, right? With as good as possible redshifts, which would mean spectroscopic redshift. But, well, what can I say? Life is unfair. We don't have complete spectroscopic redshifts. So we have to rely on photometric redshifts, right? To have as good as possible constraint, right? So we end up building our own PhotoZ catalog for this matter. What you see from many of the constraints around the literature, including LVK, at least the last time they did it, was using the GLAD catalog, which is all sky catalog, multi-purpose catalog. So we build our own catalog, which is go deeper because we just collect all available DCAM data, and it's deeper than GLAD. And also LVK analysis do fit for the BBH population. So we are not assuming a specific BBH population. The BBH population does affect our selection function, so we have to take this into account, but we are not fitting for it like LVK does. So the GLAD catalog, for instance, is complete up to 37 megaparsec, which is quite shallow, right? And
Sorry, how to measure the photometric redshift? But
I'll show you how do I measure it. So we made this initial selection in 04. So this is the constraint we did in 04. Okay. which is going up to 1,500 megaparsecs. We kind of stop around this. After this, you would expect to have a lot of incompleteness in the catalog. We are limited by magnitude 21st to 22. And you also, you can start seeing the effect of omega matter, which is now fixed. So we end up stopping like this. You also stop at the other thing that happens is you not always have a coverage of the whole sky, right? You are not kind of all sky catalog. You have to define where to stop. Most people work with 90%. We went up to at least 70% coverage to keep the constraint going on. So we select these events up to this event around here was considered in previous papers, some of them by myself and collaborators. One thing that happens is LIGO often send the updates in the maps. So we have to update, I think was these last 3 ones. And we add this new palettes, as you can see here.
What is that FAR, sir?
Sorry?
FAR.
False alarm rate.
Oh,
So we made this selection. We also evaluate, this is our alerts from this season, this LIGO season. So one thing that can happen is they might not survive until the final catalog. As you can see, events can be retracted. So one of the things that we do using FAR and other measurements available is reproduce the cuts to look in the first detections in other runs, like this previous runs, and see what survived to the final catalog and try to reproduce this, right? So we can have a more secure events. So we select these events and we produce our own PhotoZ. So how is done? So as many people might heard, I'm an AI person. I do AI for a living, mostly. So we collect all the fields that are public in DES. So we are part of a collaboration called DELV, which pretty much complements the area coverage of Dark Energy Survey. So we get the catalogs from them. We also got catalogs from the Legacy Survey, and we produce our own PhotoZ. How it's done is we use an AI method. It's a recurrent neural network, so it's adapted to work with sequences, and we treat as a sequences, like we have the filters. And we derive it, use a mixture density neural network in the end, which would output us a PDF. And why it is important? Most of the constraints you see around, they only rely on the best fit values of PhotoZ and the errors, right? So we end up using all the information available, which is the full PDFs.
You stack them, bro. You
Sorry?
stack on the PDFs?
No, it's individual PDF for each galaxy. I will show you what is the implications of this later on. But one of the reasons people don't do it most of the times is because it's hard to keep track, to make a catalog and to keep everything stored. So we have this AI lab in Rio de Janeiro, so we can do it, and we keep this. It's likely one of the current biggest catalogs of photometric redshift catalogs around, right? But this was published this year by my PhD student, Gabriel Teixeira. And for storage, which is a main issue when having so many galaxies, we developed another AI to compactify the results. So
The PDFs.
yes, the PDF are compactified, and you can produce them on the fly if you need it.
so Clécio, if you go back 1 or 2 slides, the errors on the distances are of order, 10%, something like
Yeah.
this. And if you go now, the next one, you have a sigma in matter of about 3% there. So for sure, spectroscopic would be overkill because of the error in the distances, right? So at which level of PhotoZ is it enough because you might never get a really complete spectroscopic sample, but you can get a complete, much better photosynthesis sample. So when do you saturate that? When do you reach that point?
Yeah.
1%, 0.5%?
That's the question I'm trying to answer right now. In the last slides is the work by Viviane Alfradicchi. I think you know her, right? So she's trying to get this exact answer. So we are doing this with the magnetic field simulation, producing the catalogs. And people usually attribute an error, a simple Gaussian PDF over this fake catalogs. So what I'm doing is I'm putting the whole catalogs inside the same machinery, the fake catalogs, to derive the same PDFs and try to understand how good is enough, and adding more bands and so on. So you have this, I hope you have this answer. But yeah, that's a question I have.
One question, sorry. Regarding on how you get the photosynthesis, sorry,
I'll go more with this. Well,
regarding how you get the photosynthesis with the neural network, what information do you feed to the neural network? Is like, is clustering with the other galaxies that you want to infer the redshift from, or is it the bands?
what we'll see,
Yes.
the bands, is the bands and the colors.
Okay, so you use the colors of the galaxies to learn and then use them for the one that you don't have. Okay.
Yes, for now that what we do. The mixture density is a mixture of Gaussians. You have several Gaussians. You can weight them and obtain your photosynthesis. So this is one of example of this photosynthesis. So this is the PDFs in blue. The spectroscopic redshift is here in red, and the Gaussian approximation
You
is
can have catastrophic redshift.
this one.
You can have catastrophic redshift classification because
Yes,
it's bimodal.
we have this bimodal. It's one of the examples. Here you see that the Gaussian approximation was wide in the real real PDF scenario that we have. So
So
this.
what is the training set?
What is the training set? We work on the big compilation we had from people in the ES that they released it. And later on, there was a Claudia student, Laerte student from S Plus, who made an even bigger compilation. We are using that, the Eric Lima. It's a public compilation of specs. So this is one of the runs. The quality varies because we do different cuts. Sometimes one of the things I didn't mention is, well, the models do have a different coverage. There's different coverage in the field of DCAD. So this is one of the issues. There's the sample is highly homogeneous, right? So we have to certify that we are doing the right thing while mixing everything. So we produce models specialized in 3 bands. For instance, if you have a 3 band, we produce a model for 4 bands, for instance. And this is cutting in the end of what we need. It was redshift 0.6, which is the upper limit of the distance we had. Using the PDFs, we can also perform another test like the PEATS test, which can help us understand if our PDFs are overconfident or not in some of the parts, some of the measurements, which in the ideal case, it would be overconfident at all. And you can see the trend for lower redshift. So something we can do using the full PDF. So we have odds and you have all this kind of stuff you can do. So this is the overall quality of the photosynthesis. So in terms of bias, sigma-med and the catastrophic ones, they are quite compatible with the VR 10.1 from Legacy survey.
Class, I have a question.
Yeah.
Sorry. So your neural network seems rather shallow and like you only have 2 layers and the width is 16, so it's a rather small neural network. How can you encompass like so many features which is such a small network?
No, it is not. It's just a illustration scheme. It's bigger than that.
Okay, because in 2 slides. Okay.
Yeah.
So that was
Just,
not the
yes. I mean, the point is,
yeah, because
I
here,
didn't
yeah.
open. Yes, there was more than that. It was a geodetic scheme here. Set first.
Sounds good. Thank you.
So how many hidden layers you have?
Oh, you have to ask Gabriel. Well, one of the things that we do is we put this to the machinery for, well, sometimes even for a month for optimization of hyperparameters. And by the end of the day, the algorithm tells us how the architecture should be like, right? We say what we want in architecture, right? But they define the final architecture, right? So and there's a different versions of it. There is a just to inform Vivian and others. There is a Delphi version for it, optimized for Delphi. There is another version optimized for the legacy. There is a version optimized for 4 bands or 3 bands. So it can vary. It's just a schematic idea on how it should look like, right?
So I
Yes.
I don't know much about this, but I heard there's another another algorithm called the flex boost, I think, to determine photo Z's. Is that all?
There's many.
But it's also okay. So neural nets
Yeah.
are using different algorithms.
Yes.
Yours is different.
Yeah, we build our own and try to optimize it for every niche that we have. So the idea is have control over everything and make it uniformized, right?
Is AN and Z still in the market?
Yes, it is. And it's sometimes used as a benchmark. I might be wrong, but I think we might be using that paper as a for sake of comparison on Gabriel's paper. So where was I? So this is one of the trends that we look when we see dark sirens, which is the overdensities, right? Because the regions with overdensities are likely to have a more weight in our analysis, right? So one of the things that we see in this posterior from dark sirens are multiple peaks, right? And sometimes multiple peaks are related to specific to overdensities that we see in the line of sight. So we always do this check to have an idea on where the posterior should look like in all the events. This is an example of 6 events. 5 of them are new, and one of them was a rerun after updated map. Right?
So for the NDZ, for the redshift distribution, then you stack the PDFs, right? Or not?
Not in the analysis. I don't. I consider every PDF.
But the NDZ is a
Yes, yes. The NDZ. I'm doing this here. I'm just stacking and looking over this is here.
So here's the stack.
Just to have an idea on where the overdensities are.
Okay.
Right. So so this is H naught around 7. If H naught was around 70. That is where this should be the host galaxy, and the errors from the luminosity distance from LIGO, right? And you can see it's fairly maps to where the overdensities are, which are where most galaxies are. So it's a fair.
So
it's hard to see.
What is the vertical line in the band? Sorry.
Sorry, the vertical line is where the host should be, where the host should be. If it's centered on the best value from luminosity distance coming from LIGO. See? So LIGO gave me a luminosity distance. Let me come back here.
So, and then
Oh, sorry. What's
so
more?
I use the luminosity.
Giving luminosity is here.
Right.
If I map to photo Z, to Z, sorry,
So you're.
and assuming an H naught like 70,
Okay.
where it should be, where the host should be, you know?
So, you are using also the angular precision on LIGO or use
For
you
what?
ask the angular, yeah, the direction you.
For the analysis, I do use the angular, the angular position because different angular position have different luminosity distances,
Yeah.
right? Yes. But for the sake of that plot, I didn't.
Just luminosity.
Just
That's
just the average luminosity distance, right? Which is a single one from that table that I showed you.
And the arrows.
And the arrow.
So the purpose is not to find what to candidate for the hosts. Yeah, I mean,
Oh, sorry, I
I
didn't
perhaps I got lost on this point because.
here. So there is an average luminosity distance. That's the one I use in that plot.
Yeah.
That's that. But yes, you're right. Every position, every direction in the sky has a luminosity distance. And this is taken into consideration to the galaxies on that direction.
Yeah. Oh,
Okay, so you of course don't ever find a galaxy, which is the host, because there are literally millions of them, right, in that volume.
We
But
never find a
right,
galaxy.
you never find the actual, that's not the point of the method,
Yeah.
right? But you, when you get these errors, there, you just fit a likelihood that's literally those a distribution which is centered on that distance and with those skewed error bars. And the same for the area, you weight the areas by a Gaussian fit to the error in the
Yeah, the
angular
losses
position. How does that do?
Are, this come from LIGO, right?
Right.
From LIGO, yes, they
You
are.
get the PDFs from LIGO, you get
The PDFs comes from LIGO
Oh.
and the map has a position in the sky and every position in the sky has its own PDF of the luminosity distance, which are Gaussian.
for their Gaussian.
Yes, in each pixel, right? Each pixel has a luminosity distance associated and this is pretty much Gaussian.
Ah, okay.
like this, about the live with that.
We're back. You're loving this table, right? Yes.
It's because here you have the error bars, but for these unpublished results, you also have the full PDF. Or the.
You have the what?
The full PDF.
The full PDF, yes,
Yeah.
this is within the map that I was explaining to you how, yes.
Okay, so you have access to the. full
Yes,
PDF.
they give to us in the alerts, they give us in the alert and they also update this when they do the final catalog. When it turns from super event to an actual GW.
Yeah.
When we hope they will never retract again.
Yeah.
But you don't have the masses, right?
No, the mass is only in the final catalog. So we have to wait to LIGO finish their analysis. So,
Right, so going back to the last, so what is the take home message of this?
take home messages, well, I see over densities where the most likely region to be the host galaxies, which is something I would
The first,
expect.
we don't see an
Yeah,
overdensity.
it's not an obligation, but it's something we should expect in most of the cases, simply because there's more galaxies there than the other places. And still, this is an overdensity. It's not the highest overdensity, but it is still an overdensity there. So we just do this as a cross check because we can see sometimes the peaks going into the posterior by the end. So this is some of the examples of the posteriors you have of individual events. They are very uninformative, as you can see, right? So here you see the ones using the full PDFs. This is that we are using. They are in the Gaussian approximation and using the public legacy data. So sometimes you do okay, whatever photo Z you use.
Wait, what's the x-axis?
Sorry, is the posterior? Oh, sorry, I missed it. Is because we do this blindly. Oh, so we don't know the H0 value at that
That's the
point.
good thing of lighting.
Yeah, yes, yes.
True light.
Yes, it's true blind. When we do this, in order to avoid ourselves to trying to move the photos selection somehow, we do this blindly. We look at the overall shape of the PDFs to understand what's going on. So because sometimes we are inclined to choose some PDF catalog than other, so we keep this as fair as possible.
But it is H0, right? Something related to
It
H0.
is H0, yeah, it's H0.
You
But is it like,
know the values,
you don't know the actual values?
you don't know the values, but H0, and you can see there's a peak in some.
Yeah, but is it like from 0 to 200 or from, I don't know,
Oh,
30 to
It
90?
should be somewhere around 20 to 120. Okay. So what you see here is if you, for this event, for instance, no matter catalog you use, you're doing okay. Everyone is agreeing on the procedure for this event. Sometimes things go ugly, as you can see here, right? And it's fair to say that we are using catalogs that came from the same data, DCAP. Okay, so we're not even using a different catalog like Glide catalog. So see the public legacy doesn't get it, very informative PDF. And we made some checks on the quality. We are convinced that our processing was good. And most of the cases, the Gaussian approximation also works good, which is okay, but have slightly differences, as you can see in some of these plots.
Right.
For instance, here the tail is a little bit lower, which can help us sometimes using the full PDF information.
And then you stack them, right, to get the H0.
You are obsessed with this.
But it's stacked, you have to stack them, right?
Well, you combine all the individual PDFs, as you can see here.
So you combine all of them.
Yes,
That's.
this is the individual ones.
Why would you want to use the Gaussian approximation if you have the full PDF?
Oh, we are not using Gaussian approximation, it's just for the sake of comparison.
So this is the full PDF.
Yes. All the events we were testing.
Which one is the combination?
No, there's no combination yet.
Not yet.
Not yet. It's just suspense.
Suspense, and it's not blinded anymore.
Yes, not right. It was in the paper. It was not right. So this is the constraint we got. So here is the, this greenish one or bluish, depends on how you see. For my eyes, this is green. My definition is if it's beautiful, it's green. So it's greenish thing here is our constraint. Okay. So for H0, and the others are combinations with the other measurements. For instance, GW17 or 817. So our best measurements, final measurements is this black. I think everyone agrees with that. The black curve. And this is Planck, and this is shoes. Okay, so that's what we obtain here in combination. Yes, we still don't know. That's the question. If you think about 67 or 60%.
So VLBI, so that reduces the uncertainty in the distance to the kilonova 2017 by about 30–40%, something like this,
Yeah.
right? So is this, that one is very close to us, right? So how viable is this for the ones which are 100, 200 megaparsecs away? Still viable?
Yeah, I don't have the numbers, but I don't think it would be viable. There's many things that happen in this kilonova that are unlikely. Not only it's close, you could constrain the jet, the superluminal motion of the jet, which is really hard, and it depends on several assumptions of modeling. So yeah, I don't think it's gonna happen again in the same sense, right?
So by the way, is this because you're constraining?
But the radio,
Sorry, but basically you're constraining the angle, the inclination angle of the binary there with the VLBI, right? So how is this model dependent in any way, or is it really a robust?
Yes, it is. You depend on the astrophys. You need to understand the geometry of the merger.
Of the
So,
geometry.
yes, it is. So that's one of the weak parts of this analysis when you combine everything together. Yes.
So if I don't use VLBI for the kilonova, then it's the dash red, is that it?
The bright host. Yes, there is the red one.
It's the red dash.
Yeah, the red dash.
All right.
Exactly. So you can see the numbers around here. So what's the message from this big table compiling the measurements we have on H naught? So the first, let's start with the GW17 right? So the most reliable in the sense that you don't need to do any fancy astrophysics, which is this bright peculiar velocity corrected. You have something like 18% precision on that measurement. Okay, so that's one bright siren. If you use the catalog method, which is the one I show you, is this 15 one is 69.9, which is 18%. So
Why only 15 dark sirens?
because of the selection I did selection not to get very far away sirens. I need to have coverage. I need to have a good quality photosys. So everything put in line will end up selecting 15. Not this is fundamentally different on what LIGO does. He did in last paper, right? He put all the BPHs they had, but most of his constraints do not came from the catalog itself. They claimed this in the paper. The constraint came on the fit on the BPH population.
But also the selection effect. I mean, now you have 18%, it's fine, but can it induce in the future some bias?
Yeah, we do this. We do many simulations in order to construct this selection function over the selection we do in the events. We simulate exactly if the event that will be detectable and so on. And this part is somehow weakly dependent of the BPH population. So what we do is we assume different BPH population models to produce different selection functions to see how does this impact the analysis.
Well, I have a really basic question. So you had in the beginning this the luminosity distance for each candidate that you selected.
Yes.
And if I understood correctly, from each of these luminosity distance, you derived the redshift based on some cosmology.
The luminosity distance came from the LIGO map, right?
Right.
Yes.
And then you
That's
translated that into redshift using some H naught value.
Matter of fact, you translate the Z to the luminosity distance given by cosmology, right?
Yes.
And then you fit for it. You can
And then you fit using the galaxies that are in the field.
all the galaxies in the field.
Okay.
Assuming they are equiprobable hosts. They are not equiprobable hosts because they are in different directions with different probabilities, right? Different directions and different positions in the volume, right? The position in the volume will give the right amount of how this host is likely or not.
So the weight is given by how far or
How consider the LIGO map, right?
yeah.
How likely is that position in the sky, and how far away is in the luminosity distance on that position in the sky? See, we are waiting in the volume.
And the all galaxies are equally probable to be the host, or is that something?
Yeah, before this LIGO constraint, yes. So this is something up to debate. Many people, well, are fairly arguing that we should expect to have this merger in certain types of galaxies or not. So weight by stellar mass is something people have been doing, and I'm considering this too. But still, don't know that much about the population, the host population. So that's the thing.
So what are the systematic errors that go into this?
So up to now, we assume that the systematic errors are lower than and what we see here, right? Which is the errors arriving just by the
feed.
yeah, the feed. But I'll give you more hints about this later, because now we're gonna have troubles when we work 15 dark sirens. By the end of the 04, this number will increase a lot, right? So now is the time where we start expecting to have a fair amount of systematic playing an important role there. But the bottom line is 15 dark sirens, you could reach a precision somewhere around the bright siren. One bright siren, which is okay since, well, we only have one bright siren. And the way of reducing this is either improving the dark siren or, well, people in this room have other ideas, of course, but up to now, or getting the constraint on the viewing angle of the only known bright siren, right? So that's one of the things. Oh, and sorry, and the final constraint, if you combine everything, is this one, a 6% measurement, around 68. Which is still not enough to say a lot about the tension, but it's as far as I know, is one of the most constraining results in the current literature.
And in this, are there any model assumptions for converting distances progressive or not? So it's
like the CDM with a fixed where we fix everything to plug except each cost. So we fixed omega matter.
Have you tried, if you fix all the other parameters to another cosmology,
Well,
how might it change?
we did around the omega matter, which is likely to be the variable can have impact in our analysis. And there was no significant shift. There was a shift in the peak. Is it the paper? I don't remember right now, but it's less than 1 kilometer per megaparsec in the dark siren constraint, which is way below the error bars, right? So we did that with, I can say, with many values of omega matter until I think 5 sigma of like cosmology.
But for very low redshifts and low small distances, so
And
the matter
shouldn't.
really doesn't matter that much, right?
Yeah, but we always need to cross check. but yeah, but that's the assumption. It shouldn't matter anyway, as it didn't. Oh, I will skip this one. I was about to use this one. So the next step is, well, as Rogério already mentioned, the system axes are likely to play an important role right now. We are making a couple of some assumptions. So Alfredique is Viviani is working with me. So we are now using the magnetium full hydrodynamical simulation with baryons and dark matter, deriving catalogs for it. And we are trying to understand the errors in the velocity distance, how they can affect us, how the photo Z errors are going to affect us, how different assumptions over the hosts can affect us. Right, so that's the 3 things that we are considering right now. Okay, one of the things that we are finding is maybe we shouldn't go very deep in terms of redshift. So events that are around the 0.2, 0.3 are not very informative in our simulations. We do full bi-star simulations, so we produce the map. Just the same map that, in the same format that LIGO gives to AutoNet, we reproduce the same simulation, use their own, theirs library, right? So it's very consistent about this, okay? So we are using 5,000 square degrees area and trying to understand how this affects us, right? So what do we see? One of the things is, well, weights. Right, like there's more likely hosts with more stellar mass are more likely than the others. We are trying to see with 100 events, which is likely we are going to stay away from this in 04. Well, there will be more than 100 events in 04, that's for sure. That's not the question. But as you can see, after all the selections we do, we end up with 15 good events to make this dark science. So we are doing the simulation with 100 ones now, which is fair compared to what we have now, to see how it's going to look like, right, in the future. So if you select a golden sample, like 10 degrees area, which is very small area or gravitational wave localization, you will end up with mostly unbiased sample, no matter what weights you consider. The weights doesn't play a significant role in terms of biasing the results. You may notice that sometimes there are two results for each line. This is a different choice of selection functions. Okay, so we are pretty confident that even cutting the magnitude, well, we're still making cross checks. We're still good if we have the very best events. Okay. It's the one we are using. The things doesn't go that nice if you go to events which have bigger area, like 100 square degrees. You start seeing some biases related to the choice of a population. So, for example, if you assume that the more stellar mass galaxies are going to be the host, and you make equal probability, you start seeing a shift, as you can see here. It's beyond 1 sigma, the 70, which sorry, I didn't mention that. The right input is 70 in this simulation. You start seeing the shift towards the lower values in 100, with 100 events with this. So we are working on how to deal with this. But if we keep the very good, great ones, you're still okay.
Yeah, that shows a 1.5 sigma bias. But if you do again the simulation, you recover the same bias again.
Yeah, that's something that is currently running.
And maybe it's a fluctuation.
That's exactly what I said to Vivian a week ago when she showed me this plot. We need to run many times to see if how the bias is true or not. Right? It's take some time. The simulations are quite heavy. But anyway, and this is the errors in the Z. Oh, sorry. This is the color coded for the distance of each event. So I think I spend all my time here, but I still have some things that I could tell you.
That's the chat.
Well, you have 10 minutes still, but
Okay. Okay. So
There's also a discussion session
okay.
in the afternoon.
So there is not only dark and bright science. As you know, there's spectral science. Some of you might know the spectral science. But early this years, I proposed a different perspective with my colleague Antonella Palmesi. So the thing is, we didn't see any counterpart from the BVHs or from neutron star, black hole, which are even rarer, right? But many of these BVH hosts might be in AGN disks. And when the BVH happens inside the AGN disk, this can affect the outcomes that we might have, right? So the constraint says, you say 25% might be in AGN disks. Some people claim that between 20 and 8% can happen in AGN disks. Okay, if this is true, right? There's several possible scenarios. This is a compilation done by my PhD student in the dark who made this. He likes to do cartoons, so it's a possible scenarios depending on how the merger happens. This might not come a flare, right? A BVH flare. So this is some of the models, Tagawa, McKernan, and the other two from my other supervisor, the postdoc, Rodriguez Ramirez. where you produce a cocoon inside, the merger produces a cocoon, the cocoon expands, and it goes outside the disk, and this might be visible in UV and visible light, okay? So these are possible scenarios. Other scenarios says remnants could travel through the disks and produce other kinds of off-centered flares in AGNs, okay?
Sorry, I don't quite get it. So you're saying that you get your binary black hole there inside the
And AGN disk.
Now you stir it up. Now, what is the emission? Because the emission, so you're saying that this is coming from the accretion disk, from the outer thick disk or from the inner?
It must be a thin disk in order
Must be a
to,
thin disk,
yes, in order to pops up the flare, yes. That's one of the assumptions of
So it
each of
cannot
the
just be on the outer layers. It can be, it has to be way inside the AGN, maybe.
So you need, yes, it needs to be a thick disk. It cannot be obscured by the disk. So there's several things that needs to happen in order to possibly see this flare. But this is a scenario that's been explored by many people because, well, it will turn essentially a dark side into a bright side, right? If this is true, right? So even if it's true, it will be super
What
hard.
about the masses? I mean, you have when it's a neutron star, and it's a black hole, you have different masses, right? So this criteria that tells you it's a black hole and not a neutron star.
Yeah, but we are not relying on the masses to
To distinguish between bright and dark siren.
no, the mass information important to know if it's a BBH or if it's a neutron star, right?
Yes.
When LIGO makes an alert, he says how likely is to be a BBH or neutron star. This is the information enough so you should know what to search. If you're looking for a BBH, for instance, you can look only to AGN's flaring at the time. You know? They don't give you the mass at promptly. They just give you information to search in the sky as fast as you can. Use it for it.
I thought that when people spoke about bright sirens, neutron stars, and dark sirens were black holes.
Yes, essentially, yes. So what these people are proposing, Tagawa, McKernan, and other searchers proposed by CTF, is there is a possibility that if the merger happens, the big age merger happens, inside a thin AGN, this could induce a flare in the AGN, and you can observe this variability.
Can I just suggest we postpone these for discussion?
Okay, because we can move on super quickly. Unless I need to stop now.
Yeah, maybe. How many slides?
I don't know, but I can be quickly. So the idea, I'll move very fast. So the idea here is the following. You don't have to identify the flare. You look for all the flares in the sky, monitor the flares in the sky. You assume one might be the flare you're looking for, which is the flare related to the BBH. Okay, so you can model this. Assuming there's a background flares and one possible signal flare. Okay, so the details you can see in the paper, but if you make this assumption, there is a lot of background and one might be it or just background. Sometimes you just find background, and this is still considering the modeling. Make this huge simulations that I showed you before. You could, in principle, retrieve this precision on H0. This precision depends on the number of events, as you can see, and depends on how many of those, the percentage of AGNs that do flare, or BBHs that do flare, right? If it's 5% is this curve, this is purple curve. And if it's 30%, which is huge, I don't expect to be that big, but it's under possible and reasonable constraints in nature, this could be up to 2%. If you have A+ design sensitivity, which is the next run of LIGO, okay? 500 events, next run of LIGO. So that's what we found out here. The not so strong lights is a change in the number of AGNs in the field because there's a huge uncertainty of the number of agents that's in the volume, right? You have different number density of agents. This is our procedure that we have. So, the chair is looking with the bad eyes. And the bottom line is, even if only 5% or 1% of the agents of the BBH do flare, you could still have 20% H naught if you have a full coverage of monitoring of a flare up to magnitude 21-ish, 22-ish in the sky. Okay, so that's the thing. Another good thing is you could retrieve also the precision of the number of BBH that can are hosted by AGNs, which is a big unknown, right? So what are the hosts of these BBHs? Moving on. This is just to show you another possibility. If you do not find, if you still have only kilonova, what else can you do? You can make SPI and obtain more constraints in the viewing angle, like how we said before. So this is a student of mine that's doing this as we speak. He's modeling with a huge number of parameters, the kilonova that we know, so we can obtain more astrophysical constraints on the viewing angle. So I'm just finishing right here. So that's the bottom line, right? The accelerometer requires high precision photo Z, very complete catalogs, and the legacy survey is doing the job. Rubbing can do the job in the future. JPass can be interesting because I have 50 bands, 56 bands, right? So 15 events, 80% precision is more or less equal to JW1717. We can do more. This is dark stars are interesting because BBHs outnumber at least 2 orders of magnitudes for the number of BBHs, the number of kilonova, right? And yes, now we are in the point of investigating the systematics. How the catalog completeness changes or resolves the host impact and the photometric redshifts, right? That's all I have to say. Just to finalize, as small propaganda, there will be a hackathon in CVPM about AI and astronomy. So if you know people are interested on working on that, it will be on this March. Yeah.
So we had a few questions, so I open for another couple of questions. So, yeah. Me? All right. So Clécio,
Yes.
you were looking at completeness of your catalog in the beginning there, the talk, but that was in the context of photometrics set catalog, right?
Yes.
So what would you rather have, like 10 times more complete photometric catalog, or a 10 times less complete spectroscopic catalog for this test?
Well, there is only a siren.
Because
Maybe
you don't really care about the exact galaxy that's doing that job.
Yes,
right?
exactly. So, there's only one paper using specifically DENSI, SPEC-Z for an event, right? And yes, they don't do great. So in terms of constraint. So yes, if I had to choose today, I would advocate for more complete and precise photos as possible. I think that's what you were expecting, right?
No, I have no idea really. I'm just asking because
That's my bet in that sense. Because completeness is a huge deal in terms of compared to the amount of spectroscopic sample that we have. It's quite a few. And there's also selection in the.
I guess completeness in terms of having a hole in your catalog, then I agree. But if you have anyway, like the volumes that you showed, you will have literally millions of galaxies within that volume that are candidates, right?
Yeah.
So it doesn't matter that it's 1 million or 500,000 or even.
I mean, yes, because you are mapping
100,000,
the.
As long as they are homogeneous, right?
Okay, 1,000 by being true.
No, 100,000.
100,000 should be okay. So yes, some of the tests
Why
show.
completeness then such a population?
It depends on how do you deal with the systematics in your spectroscopic sample, right?
Yeah, I was talking even.
Yeah, because
even
when
with,
you, for instance, I was participating in the target selection for some surveys in four hosts, and then it have specific science cases, and these kind of science cases are tuned not for have a homogeneous sample. So yeah, if you do have a homogeneous sample, and by the end of the day, you are doing exactly what you said. You are mapping the structure, the structure in the sky. You are not mapping the host itself. If you miss the host, so it's okay. If you have the enough good galaxy mapping the structure that you see, because you average over multiple events. So the peaks should disappear, the multiple peaks, and you end up with the right peak. So in that sense, yes. The issues have homogeneity in the spectroscopic sample and how to deal with that. Yes, I think that's the bottom line. Right? I agree.
What's the hidden price here?
It's because I didn't talk to the sponsors yet. So what's the price like?
Blended.
But we are playing a trophy.
I see no further questions, so we can head to the coffee break now and we reconvene in 15 minutes.
Okay. Thank you.
Right.